Hi, everybody, and welcome to your lesson on motion. So the state in which one object's distance from a reference point is changing, that is how we classify motion. An object is in motion if it's changing positions relative to a reference point. So I want you to think about a reference point as like your home base, where you start, okay? And if you are further or closer to where you started, you've got to be in motion somehow, okay? So to take that a step further, we're going to talk about two terms, displacement versus distance, okay? When we talk about displacement, we're talking about how far an object is away from its reference point. So for example, if I had a reference point here and then I traveled away from that reference point, that would be my displacement. But then, what if I traveled back and I ended up here? My ending spot being here, my displacement is only a little bit, right? I've only have this much space, right? This is my displacement. Okay, my distance traveled though is in red. So my distance traveled would be the total amount of distance that I walked or ran or whatever, whether it be in miles or kilometers or meters. That's the total amount of distance traveled. Displacement is how far I ended up from where I started. If you have any questions about that, just let me know. I know it can be tricky. So there are different kinds of graphs that we can use to graph motion. We're going to learn about the distance time graph today, and then in another lesson we'll learn about speed time graphs, okay? But you can use all motion graphs are useful for visualizing and communicating information about an object's motion. Okay, so distance time graphs. Remember, a distance time graph, we're calculating or we're illustrating distance over time, d over t. We're talking about how those things relate to each other. So if you see here in a constant speed, you'll see a straight diagonal line, okay? A straight diagonal line, because what you're looking at is for every distance I travel, a second ticks by. For every second that ticks by, I travel the same amount of distance. So I'm not gaining speed, I am not losing speed. For every second that ticks by, I'm gaining the same amount of distance, okay? When that line starts to swoop like this down here, I know I must be accelerating because time is ticking by, but I'm whoop all of a sudden gaining a lot of distance in not a lot of time. So there must be some sort of acceleration happening when you see that swooped line like that. Now, over here, if we see a flat line, then the object's motion must be stopped. Or paused. So seconds are ticking by, tick, 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 but we're not getting further away from our reference point. We're not getting closer to our reference point. So we know that we must be stopped. If you think about the reference point as the zero on the x-axis, so this whole bottom line, if you are getting away from the reference point, getting closer to the reference point, but you see here on a flat line, that's not happening. So seconds are ticking by, but we're not getting closer or further. We must be stopped. So pay close attention to those labels when you're looking. A distance time graph has distance on the y-axis, okay? So let's take a look at what this might be on a real graph. As I mentioned, a straight diagonal line is going to show some sort of constant speed. It'll swoop when it's accelerating, it'll swoop the other direction when it's decelerating, and a flat line is going to show us that the object is paused. So here, when we look at A from 0 seconds all the way up to about 5 seconds, we have a constant speed. It's a pretty quick speed. We're gaining 10 meters in only 5 seconds, okay? But then we turn around and we start going back towards the reference point. And now we're going, oops, this way. We're turning around and we're going back the other direction. We're getting closer to that x-axis or that 0 for our reference point. And so in B, it looks like we're probably maintaining a similar speed, but we're going the other direction. Now, at C, hopefully we know that we are stopped. We're not getting further from the reference point. We're not getting closer to the reference point. Seconds are ticking by and we are staying in the same place. And then what happens? We go away again, but this time we go away with a greater speed. Do you see how sloped this line is? It's much more vertical than this line, right? So we're gaining speed really quickly. Whoop, we go up and we go away from the reference point at a very fast rate. And then we slow down, we decelerate. See this curved line that's going the other direction? Yeah, so we are slowing down here, and then our graph ends at about 18 seconds, okay? All right, so velocity time graphs are different than speed time graphs. So we're going to put a pin in velocity time graphs. I told you that at the beginning of this video, that they're a little bit different. Make sure that you're checking your axis. Okay, so if it says velocity time graphs, we're talking about speed. We're not talking about distance. Okay, so here we are looking at a distance time graph. This is a star release question about a distance time graph, and it's asking us which table shows the best shows the average speed of the toy car at a different time intervals. Okay, different time intervals. So I know from 0 to 2, answer choice A says we traveled at about 1 meter per second. So if I'm going to go to 0 to 2, and yeah, it looks like I traveled at about 1. See, I went over 1, over 1, over 1, over 1. Yep, so from 0 to 2, I traveled at 1 meter per second. So I can keep answer choice A, but I can eliminate answer choice B, and I can eliminate answer choice C. But I got to keep answer choice D. So now let's move on. We're between A and D. And then in 2, between the seconds of 2 and 4, it says that I must have slowed down and traveled a 0.5 meters per second. Okay, between 2 and 4. So between 2 and 4. So I go up 1 and I go over 2. Do you guys remember from math? Rise over run? Up 1, over 2, right? Rise over run. 1/2. Up 1 over 2. Is 0.5 equal to 1/2? Yes, it is. So this one would be correct in this situation, okay? This one, 0.75, would not be what we just calculated on our graph. Okay, and then they both say from 4 to 6, we had a speed of 0. That is correct. We have a flat line. Seconds are ticking by, but I am not moving. I'm not getting further away from the reference point. I'm not getting closer to the reference point. So it is 0. And our answer here would be A. All right. So guys, if you have any questions about this, please don't hesitate to reach out. I know this can be kind of a tough concept for you to learn. So if you have any questions, you know where to find me. Bye bye.